In this video, let us now look at how we can prepare alkanes from halogenalkanes. But this time around, the alkanes we're going to prepare or produce are symmetrical alkanes. Now let me ask you a question. What are symmetrical alkanes? Just like the word symmetrical, alright, what it means is simply having equal division. Is that okay? So symmetrical alkanes are alkanes that can be divided into two equal parts. The number of carbons on the left will be equal to the number of carbons on the right. And how do we identify symmetrical alkanes? It's a simple one. The number of carbon atoms there is even number. So can we quickly mention some symmetrical alkanes? Ethane is one of them. Propane is not. Propane is 3 carbon, odd number. So butane is the next symmetrical number or symmetrical alkane. The next one will be hexane. The next will be octane. The next will be decane. Is that not so? Alright, because those alkanes, they have even number of carbon atoms. So we know what a symmetrical alkane is now. So how can we prepare symmetrical alkanes from halogenalkanes? The name of the reaction is known as the Wurtz reaction. The Wurtz reaction. So Wurtz reaction is used in obtaining symmetrical alkanes from halogenalkanes. And how do we carry out the reaction? All we need to do is to react ethereal solution of halogenalkane with sodium. Ethereal solution of halogenalkane with what? Sodium. When you just hear ethereal solution, what does it mean? A solution of ether. Is that okay? So solution of ether together with halogenalkane and sodium reacted would give us symmetrical alkane. Let's look at the scheme for the reaction. Is that okay? This is our halogenalkane. We are using the alkyl iodide. You will see that often alkyl iodide will be used more because the halide of iodine is much more reactive than any other halide. Is that okay? That you learn from your inorganic chemistry, gradation of properties of group 7 elements. The elements themselves, fluorine, chlorine, bromine, iodine. The order of reactivity decreases down the group, so fluorine is much more reactive. Going down, iodine does not even show any reaction like that. Is that okay? But when you see them in a compound, when you see these elements now in a compound, the order of reaction reverses. This time around, compound of iodine will be much more reactive than the compound of the other halogens above it. So don't forget that. That's why we use more of iodoalkanes here. Alkyl iodide. So this is our halogenalkane, 2 moles of it reacting with 2 moles of sodium in ether. So what's going to happen? Bond will break at this point. And so once the bond breaks here, you know this is the functional group parts. This bond line links to this iodine. So this iodine will be released. Sodium will pick the iodine. Remember that sodium is a cation, positive. Iodine is an anion, negative. So it's just a normal thing, the law of attraction. Opposite charges will attract. Okay, so some of these things will help you to understand why is it that, okay, if this one breaks off, it links up with these and things like that. So once the iodine is picked by sodium, gives us sodium iodide, 2 moles of sodium iodide. Now look at what's going to happen. The alkyl will be doubled. Doubled because of these 2 here. And when you have alkyl doubled, the same alkyl doubled, it gives you an alkane. Now let us look at an example here. This compound is pentyl iodide. Pentyl, 5 carbon atom is pent. Is that okay? Pentyl iodide. Or you can call it iodopentane. 2 moles of it reacting with 2 moles of sodium and ether. You know that this is a halogenalkane. So what's going to happen? Like I stated, at this point you have the functional group, so it's going to break here. There will be a bond cleavage. Iodine will be given off, pick sodium, giving us what? Sodium iodide, the living group, because sodium iodide is not an organic compound. So what's going to happen to this C5H11, which is the alkyl, pentyl there? The pentyl will be doubled. So the 5 carbon atom will be multiplied by 2, giving you 10. And the 11 hydrogen atom will be multiplied by 2, giving you what? 22. So you have C10H22, and this is decay. decay a full alkane. Let me write the name. This is decay. It's a full alkane. So that's actually what happens in the Wurtz reaction, where we obtain alkanes from halogenoalkanes. Alright, now let us look at the second example there. What's the name of this compound? This 3-carbon atom. So you'll be thinking of prop. Is that it, sir? Now there is iodine there, so it's a halogenoalkane, propyl iodide or iodopropane. Once again, there will be a bond cleavage at this point. Iodine will be given off to react with this sodium, giving off sodium iodide. And then this CH3, CH2, CH2, which is propyl, will now be doubled. So what's going to happen? Let's count how many carbons you have there already. There are 3 carbons. So 2 times 3 would give you 6 carbons. Is that okay? So you're expecting to get something like C6. Let's count the number of hydrogen there. Hydrogen here, there are 7 of them. Multiplied by 2, you get what? 14. And that corresponds to hexane, C6H14. Look at that here. So that's just how the reaction takes place. Alright? Writing it on paper is a simple one. Okay, now let us quickly look at, having been done with this, okay, we now want to look at how we can obtain alkanes, this time around from alkenes. And look at a short note here to guide you. Is that okay? By catalytic hydrogenation of alkenes. That's the name of the reaction. Catalytic hydrogenation of alkenes using a catalyst. The catalyst we use is either ranyl nickel, or you can use palladium, Pd. You can also use platinum, Pt. That's the symbol. Nickel is Ni. So any of these catalysts can be used. Now we have their operating conditions in terms of the temperature and the pressure required for this reaction to take place. Now the temperature is between 25 degrees centigrade to 100 degrees centigrade, and then the pressure of operation is expected to be between 1 atmosphere to 10 atmosphere. Under these conditions, alkenes can produce alkanes. So look at the reaction here. Okay, this is an alkane. How do we know that this is an alkane? You can see the double bond here. Double bond is a functional group of what? Alkanes. So during the reaction, what's going to happen? Remember our secret that the reaction usually attacks where you have the functional group. It therefore means that this reaction will be centered at this point. At this point, this is where the reaction will face. Now, for any alkene, there are 2 carbons of the functional group. The 2 carbons between which you have the double bond. It therefore means that during the chemical reaction, these 2 carbons will suffer the reaction. They will face the reaction. They will be attacked by whatever you are using as a reagent. Alright, now look at the hydrogen gas. When you're carrying out catalytic hydrogenation, that reaction is actually a reduction reaction, but a special form of reduction reaction. Not the case you use all these other reducing agents, magnesium amalgamate and all. You talk about zinc and hydrochloric acid or lithium tetrahydroaluminate 3, or you talk about the use of Grignard reagents. No, those are not the reagents you use in this case. In this case, you use hydrogen gas. It is a reduction reaction because you know that reduction reaction is the introduction of hydrogen into a compound. I hope you're aware of that. In your own level 1, you can define reduction as introduction of hydrogen, removal of oxygen. While oxidation is introduction of oxygen, removal of hydrogen. Now, the fact that we are introducing hydrogen here, it is a reduction reaction, but a special form of reduction reaction. Since it makes use of catalyst, we call it catalytic hydrogenation. Please take note of that so you can differentiate between when you are introducing hydrogen gas and when you are introducing hydrogen atom from reducing agents, which we mentioned them earlier. Is that okay? In a previous video. So let's come back here now. During the reaction, what's going to happen? This hydrogen will split into hydrogen radicals. See these hydrogens here? They will produce hydrogen radicals for us. Okay, one of them, something like this, and then the other, this. We call these radicals. They are reactive species. That is why we need these condition for the reaction, because to bring about all this split. Then at this point also, you know that this double bond contains pi electrons. So what's going to happen? This hydrogen gas will attack this bond. Is that okay? Normally this part will be broken also to give us free radicals at this point. So you could have something like carbon carbon, and then this radical there, this shows electron, is that okay? Linked to the other carbon. You notice that one of the bonds has been broken due to the formation of the radical. So what is now going to happen? One of the hydrogen will attach itself. Please, this is CH2, so let me put it CH2. So one of the hydrogen will attach itself to this CH to make it CH2. You can say that here. Then your single bond, because the double bond has been broken to single, then this CH2, it's reactive, because of this electron here. Then the other remaining hydrogen will attach there to give you CH3. Did you take note that these two carbons here, they remain the same in the product? It is the two carbons of the functional group that actually faced the reaction. In the next video, we're going to look at how you can obtain alkanes from sodium salt of alkanoic acid.